So, as said, we will consider few examples to further illustrate these concepts of transformation, and the first example that we will take is a very simple one, in which we will be transforming certain streamlines from one complex plane to the other, how the streamlines look like. And for that we will consider the simplest possible streamlines, the uniform flow. You know, the uniform flow is given by straight streamlines, all streamlines are parallel. We will apply a particular transformation and see then what happens to these uniform flow streamlines. Okay. So, let us consider that in the physical plane, that is in the z plane, we have a free stream which is uniform, and consider the stream flow is parallel to the real axis or parallel to the x axis. So, in the z plane, we have the streamlines, we can show only a few streamlines. Okay. With speed u infinity. So, the streamlines are what? The stream function is u infinity y, okay, and the streamlines are given as u infinity y equal to constant. Or simply y equal to constant. We apply a transformation zeta equal to 1 by z. Apply the transformation zeta equal to 1 by z. So, how will the streamlines look like in the zeta plane? Yes, hyperbola. How the parallel straight line will transform to that? Zeta equal to 1 by z, okay, or we can write that is and equating real and imaginary. Now, on the streamline, what we are basically doing? We have to transform these curves, these straight lines to this plane. Now, transforming a straight line is basically transforming certain points. So, how each of these points are transformed, that is what you have to find. Now, the points on the real plane, or sorry, the point on the physical z plane are characterized by y equal to constant. Say for simplicity, let us write k. Now, if we want to transform these streamlines, then this y is constant k. So, we can put y equal to k here. So, sorry. Eliminate x from these two. Oh, sorry, yes. If you eliminate x, what do you get? Simple. From the second relation, find x, put it in the first. What it is? J square plus eta square. J square plus eta square plus what is it? Hyperbola? This is ellipse? This is circle. So, on the xi plane, or sorry, on the zeta plane, these uniform flow streamlines are circle. circle with radius and center what? Circle with radius where? Circle with radius circle with radius how much or center? Center at center at 0 eta by 2k. Yeah, it should be 1 by 2k. Okay, and radius 1 by 2k. So, for each value of k you will get a circle. Try one more, this time again uniform stream, but along the imaginary axis, a uniform stream along the imaginary axis, and the transformation is 1 by z square. Transformation is simply z square. Uniform stream along the imaginary axis or along y axis transformed by zeta equal to z square. The streamlines are x equal to constant. So, what will happen to the streamlines on the zeta plane? parabola. Xi is x square minus y square. Y is eta by 2 k from here. In eta equal to 2 x y, if you take x equal to k, so y becomes eta by 2 k and x square is k square. So, this becomes k square minus let us try now with okay, now try this problem. Develop a Joukowski airfoil of chord 152.5 millimeter, thickness to chord ratio of 15%, thickness to chord ratio 15%, camber 5%. Consider that airfoil is developing full Joukowski lift. Consider the airfoil is developing full Joukowski lift at 10 degree incidence in a wind of 18.3 meter per second. draw a few adjacent streamlines. Okay, that drawing part of course, we will not be able to do here, but the rest. How will we proceed? How will you proceed? Oh, sorry. How will you proceed? What will be the steps of this problem? Any suggestion? What I have discussed earlier? Since we are not in a position to solve flow over the airfoil directly, we have to transform this airfoil to a circle, what we did by Joukowski's transformation. So, the first thing is we have to find the circle, okay, along with the parameters of the transformation. Then we have to get the, we know the solution for the circle. So, we can construct the solution for the circle and then transform it back to airfoil. So, what do we want to know? We want the radius of the circle, we want the center of the circle with respect to the origin, we would like to know where will be the critical points. So, these are the things that we have to first find out. Once we can do that, we can write the solution for the circle, which then can be transformed back to airfoil. So, chord is how much? Chord is related to chord is approximately 4b, where b is the parameter in the transformation, Joukowski's transformation. So, chord is 4b. So, that gives b to be and the Joukowski's transformation becomes z equal to zeta plus b square by zeta. B square becomes 1453.5. This is what is b square, but see you should notice these things. We have used millimeter for b, implies that now this z zeta they are also have to be in millimeter. What is the radius of the circle? R equal to R is related to b, b into 1 plus epsilon. R is b into 1 plus epsilon. Epsilon is as yet unknown to us, but we have another relation, maximum thickness. What it is? Maximum thickness 3 root 3 by 4 epsilon. Okay. We have 3 root 3 by 4 epsilon is maximum thickness. How much is that? 0.15. This 3 root 3 by 4, you can remember this value is 1.299, that is what is taken, 1.299.15, that gives epsilon equal to 0.1155. Now we have b, we have epsilon, we have radius. Actually it becomes 42.53, but let us take 42.5. Now, flow over a circular cylinder is represented by a uniform stream, a point doublet placed at the center of the circle, okay. And if it is lifting a circulation, the doublet strength is given by the radius, or the radius of the circle determines the strength of the doublet. What it is? The doublet strength the required doublet strength, how much? What is the relation? 2 pi r square q infinity. What we are writing, capital Q or small q? Capital Q, no, but anyway, escape, you do not want to. This is free stream, not something different, or did I make it? This gives 0.208 meter cube per second. Now, in this case there is a circulation also, because the problem says that this airfoil develops, this airfoil has camber and this airfoil develops full Joukowski lift at 10 degree. Okay. Now, how much is the full Joukowski lift at 10 degree? Now, how much is this? This is what is given by the Kutta condition. How much is that? Four pi what? 4 pi r q infinity sin alpha plus beta. Now, alpha is of course given 10 degree. How much is beta? Beta is camber is given 5 degree. Camber is given 5 degree. So, camber is related to beta. How much it is? Beta by 2 is the maximum camber. So, we have beta by 2 equal to how much? Not 5, that is percentage. 5 by 100, 0.05. So, beta is how much? 0.1 radian. That equal to approximately 5.73 degree. So, now we can put that value. This will give the circulation to be 2.65 meter square per second. So, we now have the complete flow for the circle. The flow on the circle plane is now given by a uniform stream of 18.3 meter per second, a doublet strength of 0.208 placed at the center of the circle and a circulation of 2.65 meter square per second placed at the center. So, we can now write completely the complex potential on the circle plane. Okay. is complex potential due to the uniform stream. Complex potential due to uniform stream at 10 degree angle of attack. What it will be? Okay, forget about those numbers. Complex potential for the stream at an angle of attack alpha. You have written it earlier. You got to remember that. No. Q infinity complex potential. So, that will contain both the potential function as well as the stream function. And it is potential Q infinity z sorry not z zeta, Q infinity zeta e to the power minus I alpha, where alpha is 10 degree expressed in radian. Remember, in this expression these alphas are in radian. Plus due to the circulation, I gamma by 2 pi log we have the values for Q infinity, gamma, mu, alpha. Okay. We already have Q infinity 18.3 meter per second, alpha equal to 10 degree equal to some radian, gamma equal to 2.65, no 2.65, what we still have not done is zeta naught, center of the circle, but we have found all the components of zeta naught. What is zeta naught? Location of the center minus b epsilon plus I r beta. Okay. Actually I r sin beta, you can do it r beta also, no problem, because the beta is really small. So, once you put it, the complex potential on the circle plane is complete. You now have complete potential function on the circle plane. both potential function as well as the stream function. You can take out the real and imaginary part, split it, or you can leave it in the complex potential form itself and then transform it back to the airfoil plane. I mean, after this what we did for the first two problems, that sort of things we have to do. We have to now transform back to zeta to z using that Joukowski's transformation once again. So, that of course, will be quite involved, just substituting this. So, it would be better to try it numerically. You may try that, even plotting and all numerically. Rather, I would expect that you will complete the transformation and plot the streamlines. But what I hope that you are following how to handle the problem. Let us consider one more. Find the velocity at the 3/4 chord point on a symmetric Joukowski airfoil of 20% thick, velocity at 3/4 chord point on a 20% thick symmetric Joukowski airfoil, also given alpha equal to 0 degree and the free stream is 50 meter per second. See, there are two 3/4 chord point, one on the upper surface, one on the lower surface. However, in this case it is given the symmetric airfoil and the flow is also at 0 degree angle of attack. So, the upper surface and lower surface will be same. So, locating only one is sufficient. So, where is the 3/4 chord point? Where is 3/4 chord point? Three-fourth chord point is 3/4 C from the leading edge. So, from the origin where it is? Origin is at the center, at the middle. So, it is C by 4 from the origin. So, how much is that? What is that point? Corresponding theta? Corresponding theta. You can use that relation x equal to 2b cos theta. and C is 4 B. So, this is approximately B. So, how much is theta? Pi by 3. Okay, that is the location of the point. But before that, once again we have to construct the circle and the flow on the circle. So, we will have almost a similar approach what we had earlier. What do we need to find? We need to find the doublet strength and the circulation. For doublet strength, we need the radius of the circle. For the doublet strength, we need the radius of the circle. How much is the radius of the circle? R equal to B into 1 plus epsilon, no? What is 0.2? Epsilon is not 0.2. Since the chord here is not exactly specified, we will not be able to write how much is the chord and how much is equal to B and how much is equal to R specifically. So, we will keep it as the ratio R by B is 1 plus epsilon, and epsilon can be found from the thickness. How much is the epsilon? .299 epsilon equal to 0.2. Okay. That gives epsilon equal to 0.154. So, we have R by B equal to 1.154. Okay. How much is the circulation? 2 pi r q infinity sin alpha plus beta. Okay. The circulation gamma equal to 2 pi 4 pi r q infinity sin alpha plus beta. How much is this? This is equal to 0, because for this case alpha is 0, beta is 0, it is a symmetric airfoil. Beta is related to camber, alpha is given as 0, and since this airfoil is uncambered symmetric, beta is 0. So, for this case there is no circulation, it is only a uniform stream plus a doublet. Now, what is the expression for the complex velocity on the circle plane? We can write it in terms of q infinity and mu and this, but we have other expression also. If you remember the complex velocity on the circle plane, if you remember we had this expression we earlier derived 2 I q infinity sin alpha plus beta minus sin alpha minus theta into e to the power minus I theta. Okay. Now, in this case we now have all the values. We are interested at theta equal to pi by 3, or for this particular case alpha is 0, beta is 0. So, the first term is 0, here it becomes plus sin theta only. Okay. This gives how much 2 I q infinity only sin theta e to the power minus I theta. We are not interested in velocity at all the points, we are interested only velocity at the 3/4 chord point, which corresponds to theta equal to pi by 3. So, at that point what will be the velocity, complex velocity on the circle plane? You can put this value q infinity is 50, w zeta corresponding to theta equal to pi by 3. Please check this. Please check these calculations. Simple, q infinity is 50, theta is pi by 3. Okay. Please check these calculations. Now, this is the velocity at the theta equal to pi by 3 point on the circle, but we do not want to know the velocity on the circle, we want to know the velocity on the airfoil. So, we have to find out what will be the velocity on the airfoil. We have w z equal to w zeta dz d zeta, of course, everything at theta equal to pi by 3. So, this w zeta pi by 3 already we have found, we have to find out what is dz d zeta at theta equal to pi by 3. I will just give you the final result for dz d zeta, but please check this. At theta equal to pi by 3, what I obtained is something like 1.57 plus 0.6 I. So, finally, the complex velocity at 3/4 core point what I obtained. Once again, please check these numerical calculations.
So, how will we get dz by d zeta?
dz by d zeta.
So, we don't have b value. We don't have the b value.
It will not be required. See, it is dz by d zeta is what? 1 minus b square by zeta square, okay? And it will contain only b by r. So, b by r we have. Perhaps I will show that details calculation also tomorrow for one case. And remember, this complex velocity is not u plus I v, it is u minus I v. So, what we have is u equal to resultant speed is of course about 52 meter per second. Angle also, if you want the direction of the flow in terms of angle, that also you can find.